Right. Let's see. Okay. All right. So so today we're going to talk about the Wilsonian effective action, the program of effective field theory, and some applications. So I've described for you renormalization viewed as so in renormalization we've seen that we hide infinities in infinite coefficients. We had the infinities that we obtain at loop level and the quantum theory into infinite coefficients in the Lagrangian or the bare Lagrangian, and as a result, we obtain a dependence on scale. So first, we introduce an arbitrary dimensional transmutation scale or cutoff scale or some type of scale, but finally we after introducing some normalization condition or some way to condition to renormalize. After that, we obtain some dependence on some scale. So that was one program for renormalization. But there's a slightly different take on the renormalization program, which was described by Wilson. So, by the way, so within this program, we obtain renormalization group equations, which show this dependence on scales. But there's another approach that was started by Wilson, which also results in a dependence on a scale of dependence on various couplings and masses and so on scale. One which has made it possible to relate to apply and relate quantum field theory to condensed matter physics. That part we're going to do next lecture. But in this lecture, I will define this Wilson approach to an effective action for the quantum theory that depends on a scale. Now, one of the points of this program is that in the real world, we're never able to probe any energy scale. We always are limited in our experiments by experiments or our theory by some maximal energy scale. And the question in this effective field theory program is, can we hide our ignorance about the high energy physics above this energy scale into a consistent framework? And the answer turned out to be yes, and this will define first the Wilsonian effective action, and then the program of effective field. All right, so the Wilsonian effective very simple to define. What we're supposed to do is to just integrate out the degrees of freedom with momenta higher than this cutoff lambda, and thus hiding our ignorance about it. So first we'll integrate out in a theory that we know, and then we'll generalize and see what happens if we don't know the theory above it, about this lambda. All right, so let's start with the simplest theory that that we've analyzed in 4 dimensions, lambda phi 4 theory, and the application will be to Euclidean space. It's easier to work in Euclidean space. So the action is a kinetic term with d phi squared and the mass term and lambda phi 4. And the quantum object that we're interested in is z of j, partition function, which is the integral of a path integral of phi of e minus the action plus this integral j phi, where j of x is the source. And we want to integrate over momenta higher than some lambda, so we have to go to momentum space. In the momentum space, the kinetic term, as usual, is this Fourier transform phi tilde of k times on one side and phi tilde of minus k on the other side, and in the middle, k squared plus m squared. So minus box plus m squared in momentum space becomes k squared plus m squared. And then the interaction part is lambda over phi 4, phi factorial, times the integral, so the integral of momenta, this Fourier transformed phi, so phi tilde k1 until phi tilde k4, times the momentum conservation, 2 pi to the 4 delta 4 of sum of the k's. So now we introduce the cutoff lambda in the UV. And this being a cutoff means we cannot access in experiments this energy is higher than the cutoff. That is to say that in terms of the partition function, so from the partition function we can get Green's functions and from them as matrices and so on. So we'll get to physics. So we have therefore to assume that J, the variable, the source, which is a variable from which we derive physics, is equal to 0 for momenta higher than the cutoff. So that means that the procedure now is the procedure for calculating physics using this effective action is a path integral over momenta lower than lambda, E minus some effective action now that depends on both the fields and the cutoff, plus the integral over j dot phi, j being non-zero for momenta smaller than the cutoff, but where now e to the minus the effective action depending on phi lambda means the path integral of momenta higher than lambda of e to minus the action, the Euclidean action. Now there's no j phi, as we said, j equal to 0 for k greater than lambda. And this, in the exponent here, as effective, is called the Wilsonian effective action. So after doing the path integral, the effective action will be something like, so the classical action, kinetic term d phi squared over 2 plus m squared phi squared over 2 plus interaction lambda phi 4 over 4 factorial plus all possible operators of higher dimension. So as an operator, so this this and this have dimension 4, and this has dimension 2, with a coefficient that has also dimension 2. Coefficient here is 1/2, and here is something also of dimension 0. So in general, when writing an action, we start with some kinetic term, and then we add interaction terms in the order of the dimension of the operator. So in the same way, in this effective action, we will order the other possible terms coming from the path integral in terms of the dimension of the corresponding operator. So operator O of dimension delta with index I. Now, so all of this action is up to dimension 4, is the complete one up to dimension 4, right? So this is dimension 2, this is dimension 4. And you cannot write anything else with dimension up to or equal to 4. So all of these things have dimension higher than 4. However, since the Lagrangian itself depends, it contains only even powers of phi, so phi squared and phi 4, the classical Lagrangian, also the quantum Lagrangian will contain even powers. So the next dimension after 4 here will be 6, not 5. 5 will be absent. So dimension delta greater or equal to 6, and then these coefficients will be constants, but constants with dimension, because the Lagrangian itself has to have dimension 4. So the constants in here will have negative dimension, will be 4 minus delta. All right. However, as we said, in this effective action, the momenta have to be smaller than lambda. So when we do the Fourier transform phi of x, writing phi of x as integral dk e to the ikx phi tilde of k, k is integrated only up to lambda. All right. So I wrote here the form of the Lagrangian as being the classical Lagrangian, right? Or, but of course, in reality, it's not the classical Lagrangian that appears here, but it's some renormalized Lagrangian, where we have a wave function renormalization, so a z phi multiplying phi. We have a mass renormalization, Zm, and a coupling renormalization with Z lambda. Of course, under this definition, I assumed I absorbed the wave function renormalization in Zm, Z lambda. And when writing this, when this is a renormalized Lagrangian, remember renormalized Lagrangian and the Bayer Lagrangian are equal numerically, but not but are written in a different way. Then this coefficient, these constants here, m physical and lambda physical, are defined as the one particle irreducible, so one particle irreducible contributions at some momentum. So that's a normalization condition, and we choose to be at momentum equal to 0. So then really the effective actions, once we do the process of renormalization, really the Wilsonian effective action has also these Z lambda wave function renormalization, and then where while introducing this renormalizations of mass and the coupling constant implies that so after the renormalization, which was defined, so the physical objects were defined at momentum equals 0, but now we have quantum and integration up to some momentum lambda. Correspondingly, the renormalization itself will depend on this momentum lambda. It's momentum up to which we integrate. So the coefficients here, the constants, the parameters of the theory, m and lambda, will depend on capital lambda, the cutoff scale of the theory, and also the wave function renormalization would depend on this cutoff. But here, while writing it this way, all coefficients will be finite functions of lambda, since the correlation functions of renormalized fields calculated by taking derivatives, functional derivatives from the path integral with the effective action, path integral up to lambda with the effective action, are finite. So let's calculate. All of this is a little bit abstract. This was meant to just orient you a little bit. But now let's be a little bit more concrete. Let's do an example and calculate. In particular, let's calculate these coefficients C delta I. And well, when I say C delta I implicitly consider also the lambda as C4, the dimension 4 coefficient, and m squared as the dimension 2 coefficient. The coefficient of the dimension 4 and the coefficient of the dimension 2 operator. All right, so the classical Lagrangian, or Bayer Lagrangian if you want as well, depend all on even powers of phi. So then these operators will also have an even dimension, an even number of phi's. Sorry, we'll have an even dimension because we'll have an even number of phi's, and then you can also introduce derivatives. But by Lorentz invariants, they should come in pairs to kill the vector coefficients. So they'll all be of even dimension. But in particular, let's among these operators, which could in principle also have derivatives, as we said, let's consider the operators that do not have derivatives, so just phi to the power 2n. And let's consider them at one loop. That's the simplest thing you could do. But then it's pretty clear once you draw the vertices. So you draw n phi4 vertices, and then you have two external lines for each to have this operator phi to n, and then you want to draw a one loop diagram. So it's pretty clear that you basically have to connect the remaining two legs on each vertex with the adjoining ones and forming this unique Feynman diagram. So with one loop, and then at each vertex we have two phi's going out, corresponding then to a phi to the 2n operator. Okay, but this one loop is, remember, we'll calculate the Wilsonian effective action. So we're calculating this. So that means that in the path integral that obtains the Wilsonian effective action, we'll only integrate over momenta that are greater than lambda. Whereas this Wilsonian effective action is used as in the quantum theory, quote unquote, so in the path integral, for momenta lower than lambda. So the external lines that form the operator in the effective action have momenta smaller than lambda. All right. Then the symmetry factor for this diagram is, well, 2 to the n times 2 times n. There's a 2 to the n due to the factor that at each vertex I can switch this with this. So that's a factor of 2, switching each of these. So at each vertex there's a factor of 2 like this. Then this is cyclic. So choosing which vertex I call the vertex 1 among all the n vertices is a choice 1 out of n. So that's a factor of n. And then finally, there's a reflection symmetry. There's a reflection symmetry which gives an extra factor of 2. Okay, and then of course there's the choice of momenta. How do I assign momenta to the external lines? How do I assign the momenta p1 up to, well, sorry, p2n. Why I said pn, p2n should be. Sorry about that. So the momenta p1 up to p2n, how do I assign them to the external lines? By permuting them, I have a factor of 2n factorial. That's the usual thing. That's why I I write in the action lambda over 4 factorial because to cancel most of this. So yeah, sorry, I mixed up the thing. So I was thinking about O4, but now we're looking at O delta. I mean O2n, so to speak, not n equal to 2. So in a general 2n, I write the coefficient C delta, but or C2n, but then the Feynman rule coming out of this C2n would be with minus C2n times this number of phi's factorial, so 2n factorial, in the same way as in here. So usually, so we started by saying lambda phi 4, then we divided by the 4 factorial because we noted that the Feynman rule had the 4 factorial multiplication in it, the number of fields 4 factorial. So the same way here, we say that the Feynman rule is minus C2n times 2n factorial, number of fields factorial. And this is this factorial for choosing the p's, 2n factorial, so that cancels. But then divided by the symmetry factor, which is 2 to the n times 2n. Then this diagram, oof, what happened? This diagram has n vertices. So I have a minus lambda physical to the n. Lambda physical because that's the one that appears before. Yeah, that's the one that appears before the considering the loop corrections. And then I integrate from lambda to infinity the momenta, and I have n. I have n propagators, so 1, 2, and so on until n propagators. So 1 over k squared plus m squared physical to the n. So this one loop correction means lambda to the n correction to O to n, and then their higher order corrections. So we calculate them on the first order one. Now, then if we're calculating really only these extra O's, not including the first two, then the integral is convergent, is d4k over k to the 2n. So then 2n is greater or equal to 6, so it's UV convergent. And then there's no IR here because we have integrate only from lambda to infinity. And then we can also assume that m squared is much less than lambda squared. That's a kind of obvious assumption because, well, I mean, really, that's what we mean by lambda being a cutoff. It cannot be that the scale of the mass. It must be much higher. much higher than the masses in the theory. So so then I just ignore, and momenta are always greater than lambda, so I just ignore this m. And then I have approximately integration up to of 1 over k to the 2n, and then integral d4k is 2 pi squared k3 dk. And finally, I get this. So I get the dimensional factor, which was obvious just by dimensional analysis, 1 over lambda to 2n minus 4. And then also this coefficient, 1 over 8 for pi squared, 1 over 2n minus 4. So we've found our C2n. So it's this integral, which we just calculated, times minus lambda phi over 2 dn, well, minus lambda physical to dn, divided by 2 to the n times 2n. And here we have 2n minus 4, that is 2 times n minus 2. So overall I get this, minus lambda physical of 2 to the power n, divided by lambda to the 2n minus 4. And then this numerical factor, lambda 1 over 32 pi squared n minus 2. Okay, so so this is for 2n greater equals 6. But now, as I said, I can also consider lambda and m squared as also some kind of operators, now that O4 and O2 with some coefficients that are called C4 and C2. So formally, then we have the same, we'll get the same integral. This integral will be the same, formally. So, I mean, the same Feynman diagram will be true, just that with phi 4 in here. So really, the diagram would be this. Right. Just that we need to add the tree result also to the one loop one. So minus lambda of depending on the cutoff lambda. So the coefficient of the operator phi 4 in the effective action is the tree coefficient m physical phi squared. Lambda physical phi 4 over 4 factorial. Sorry, z lambda lambda physical over 4 factorial. So the 4 factorial has been cancelled here. I mean, this cancelled trivially, like I wrote in here. So z lambda lambda physical plus this integral, which formally is the same one as here. So is minus lambda physical squared times this integral d4k over 2 pi 4 1 over k squared over m squared squared from lambda to infinity. And then yeah, and then I just substitute the numbers. Yeah, I have 2 to the n factorial over 2n, 2 to the n times 2n is now this 3/2 here. But the difference now is that the integral is not convergent anymore. Now I have d4k over k to the 4 at infinity. So that's divergent. But we know how to deal with that. I mean, that's just the usual renormalization that we did before. Sorry. However, we did the renormalization by defining the normalization condition at 0 momenta. So minus lambda physical was minus the 4 vertex at 0 momentum, 0, 0, 0, 0. And so I substitute this in here, and says that for lambda equal to 0, I have minus lambda physical is equal to minus z lambda phi physical plus 3/2 plus all of this for lambda equal to 0. Okay, and then the difference between the two is finite. So both of these two are infinite, but the infinity is in the upper part of the integration, and it's the same one, so that cancels. And so the difference between the two is finite. So minus lambda physical plus lambda of capital lambda is this coefficient 3/2 minus lambda physical squared times the integral from 0 to lambda of the same thing. And now we can do this integral explicitly. d4k is as before, d2 pi squared k3 dk. Which I write as, so I write here k squared dk squared, and then I shift by k squared by m squared physical. So I get this integration from m squared physical to lambda squared plus m squared physical of the new variable k tilde squared minus m physical squared times dk tilde squared over k tilde 4. And then I get this coefficient 1 over 16 pi squared. This is the first term is just log lambda squared plus m squared physical. Sorry, log of k tilde squared between these two. So log lambda squared plus m squared physical over m squared physical. And the second term is minus m squared physical times this integral is minus 1 over k squared. So plus m squared physical in between these two, right? Yeah, which is but m squared physical is much smaller than lambda squared. So so this would have been m squared physical over lambda squared plus m squared physical, but in the denominator I neglect this m squared physical. So it's m squared physical over lambda squared, and then minus the lower part of the integration is this m squared divided by the same m squared, so 1. So finally, also neglecting this, so I've neglected 1 here and 1 here. So I get approximately oh, and then this is also approximately 0 because, well, because lambda squared, as I said, is much greater than m squared physical. So I just neglect this thing altogether. And then I get just 1/8 pi squared. I took the 2 outside the log. Log lambda over m physical. And then -1 turns into -1/2. Okay, so finally then, we'll obtain that this coupling, depending on the cutoff lambda, is lambda physical, defined at momenta equal to 0, plus this 3/16 pi squared, lambda squared physical, log of lambda over m physical -1/2. So we see the appearance of this log. This will, phi 4, this will always appear. Then we could also, we should also calculate the coefficient of the operator phi squared. That is C for n. So the Feynman diagram then would be this. So yeah, so that Feynman diagram then is just, so rewriting it, I can rewrite it like this. Right? A line with a loop. So it's independent of the external momentum. I have P coming in here and P coming out here, so this loop is independent on P. But since the P-dependent part of the Feynman diagram gives the wave function renormalization, right? Wave function renormalization because this in momentum space is P squared phi squared, so it's P-dependent. So the P-dependent part gives wave function renormalization. And there's no P-dependent part at this one loop, as we said, just shown. So that means at one loop we have Z of lambda equal 1 plus higher order. But from this Feynman diagram, there is a P-independent part. And the P-independent part will give the mass renormalization, because that's what happens in here. In a coefficient of phi squared that is independent of momentum is a mass. And again, so we do the same thing as for the in the previous case. In this case, we write now, thinking of this as a vertex, we write minus m squared of lambda equal to the 3 part, which is minus zm m physical squared. Right? You think of this, but you think of this as a vertex, so then you put a minus sign, plus the one loop correction. And there's only one vertex, so minus lambda physical to the power 1. There's a coefficient, symmetry coefficient 2, just symmetrizing this, so 1/2. And then 2n factorial is well, cancelled. Yeah, so another way of saying it is that you have this general form gives 1/2. And then the integral over only one propagator, integral d4k, 1/k² plus m² phi squared. But the integral from lambda to infinity, and then plus higher orders. This is quadratically divergent, so at high k, this is k4/k², k². But then, also as before, the full renormalization gives, so when I integrate from lambda equal to 0 to infinity, I define the momenta, therefore I define the coefficients at momenta equal to 0. I have minus m² physical. So then minus m² physical equal to this plus the integral from 0 to infinity. And also as before, you know, the UV part is divergent, but there's no IR divergence because of the mass. So the difference of these two integrals is finite. Minus m phi squared plus m² of lambda is this coefficient minus lambda physical over 2 times the integral now from 0 to lambda. And I can easily integrate, do the integral in the same way. I write this as integral k² plus dk² over some k² plus m physical squared times the coefficient, and then I shift it to k² to have that in the denominator. And then the first term now is, in the first term, these k² cancel, and I just get integral dk² between these two terms. But in the higher order term, and then I have lambda squared plus m phi squared minus m phi squared, that is lambda squared. And in the second term, I have minus m physical squared times this integral, which is also divergence. Now it's log of lambda squared plus m physical squared divided by m physical squared. M physical should be here. So then finally, I have that m² at lambda is m² physical minus lambda physical over 32 pi squared times this integral lambda squared minus 5 m² physical log lambda squared over m physical squared. Okay, so we've calculated all of the coefficients in the Wilsonian effective action. So we can observe that the dimension is, as I said, 4 minus delta. And since these coefficients depend strongly only on the cutoff lambda, I mean, there are masses and so on, but they are much smaller than lambda, then the coefficient can only be proportional to 1 over lambda, I mean, approximately proportional to 1 over lambda to power delta minus 4. And that means that these coefficients for the extra operators, the dimensions operator starting at dimension 6, are highly suppressed for large lambda. So that means that they will not change much the physics. So having these extra things will not change much the physics. So we could just, in principle, we could just work with this, where now lambda is a large but finite cutoff. All right. So now finally we come to the program of effective field theory. So for that, we have to consider a new setup that is closer to the physical case. In a physical case, we always have some true cutoff. If nothing else, there is the Planck scale at which we have quantum gravity, for which we don't know how to treat non-perturbatively yet. But also there are other, before that, there could be other scales. And in many theories that we like for various reasons, there are. So there are things like supersymmetry scale, grand unified theory scale, Kaluza-Klein scale, and so on. All of these at all of these scales, the physics changes. So as far as the low energy theory is concerned, there is a cutoff. That's a physical cutoff, because beyond that we have a different theory, a theory that has extra fields, extra modes, extra degrees of freedom. And let's also assume that in the units of this cutoff, the parameters of the theory are small. So these, so C delta, so we've seen that C delta is of the order of 1/λ to the delta minus 4. But now I consider this true cutoff lambda 0. And so I assume that on top of things, so it's also proportional with this, but then on top of things, there's a small coefficient in here. So small dimensional number. So dimensionless number. So that is to say that C delta at lambda 0, it's much smaller than lambda 0 to the power 4 minus delta. Okay. And then the same thing for the operators of dimension 2 and 4, which are already in the theory. So lambda, the dimensionless 4 to the 5-4 coupling lambda at capital lambda 0 scale, it's much smaller than 1, and the mass squared at scale capital lambda 0 is much smaller than capital lambda 0 squared. So that means that we have a different approach. So in the approaches that we used in quantum field theory until now, we always assume that the theory is valid until infinity, and that's obviously not true. So now we're trying to do so the exercises before were in some sense toy models, in some sense academic, because there's always some physics that you don't know beyond some scale. But now we're trying to do something physical, and with this assumption that all of these, that in the units of the cutoff, the parameters of the theory are small, then we treat this effective theory, whatever it is, as a fundamental starting point, rather than assuming that there's a better definition of the theory in the UV. So rather than assuming that, well, instead of QCD, I go to the standard model, and then instead of the standard model, I have the minimal supersymmetric standard model and something else in the UV. Instead of assuming that there's, starting with a theory that we say that's the theory, and then doing calculation in it, we start with this effective theory, and we say, well, I don't know what's happening above this lambda 0, but I know that there's this effective theory which obeys these relations. And since these coefficients are small, even as functions in units of the cutoff, so the numbers in front of these things are very small, then we can just assume that they actually vanish. We just ignore them, put C delta equal to 0, and we'll see if that's consistent. But now lambda 0 was a true cutoff, but we're still interested at scales much smaller than that. I mean, for instance, if you put lambda 0 the Planck scale, obviously we cannot measure things at the Planck scale. We can only measure things at up to like 10 TeV. So we still want to integrate this theory from lambda 0 down to the scale at which we can measure. So let's integrate momenta from lambda 0, from our scale lambda up to the cutoff scale, true cutoff scale lambda 0. So then it means that what we do is we define this new Wilsonian effective action, E minus S effective of phi at capital lambda, as the path integral over this window from lambda to lambda 0 times the exponential of the minus Wilsonian effective action of phi and lambda 0. Now, since we already did this path integral between infinity and the lambda, and we can just use the formulas that we've derived. And so we use it for lambda 0 and for lambda, and then do the difference between them, and write then m squared of lambda is m squared of lambda 0 plus 1/2 lambda of capital lambda 0 integral between capital lambda 0 of this, and so on. The same thing for the coefficient of phi 4, for the same thing of the coefficient of phi to the 2 ddn. I have these numbers times integral from capital lambda to capital lambda 0. And we've even calculated these integrals, and moreover, now we know that these things are finite. So using the integrals from before, and assuming now that m squared at scale lambda 0. So the theory was defined at scale lambda 0 now. And we also have to assume that lambda is not too much smaller than lambda 0. I mean, this is kind of, well, I mean, it's not a well-defined statement, but it means that the ratio, well, should not be absurdly small. And then we also have to assume, in this case, we can put here, for instance, m squared of lambda 0. And also assume that m squared of lambda 0 is much small, so that this is constant. Then we also have to assume that this m squared of lambda 0 is actually much smaller, not just than lambda 0 squared, but also than lambda squared. In this case, we just use the integrals from before. Here I had m squared physical, which was a constant. That was the point of writing this in terms of lambda 0 rather than in terms of lambda. And also, in the integrals, we've assumed that m squared physical was much smaller than lambda squared. So now we have to assume the same thing here. Then we just take the formulas from before and find, so take, let's say, this m squared and divide. So m squared of lambda, write m squared of lambda, m squared of lambda 0, and then make the difference between the two, and then we get approximately this, the quadratic piece. I mean, of course, there's also the log piece, but log piece is will give log of this ratio squared, b squared, and I assume that b squared is not too much smaller than 1, so and when taking the log, we get even smaller, so the log is neglected in here. I just have the quadratic piece. And then for the coupling, 5-4 coupling, when I divide between this, I subtract the scale, the value at capital lambda from the value at capital lambda 0. Then this constant cancels, this constant cancels, and we're left just with the difference of the logs, which is just log of this thing. I mean, this is now small, but this is still leading now in the difference. And then in the higher order operator, I get just this coefficient times the difference in this dimensional object. So 1 over lambda to the power 2n minus 4 minus 1 over lambda 0 to the power 2n minus 4. And we note then that lambda 0 is not very important for these higher order operators, right? We said, this is a high power, and then lambda 0 is greater than lambda, so this coefficient, this object is smaller than this. In fact, it's much smaller since the power is large in general. So we can, so because of that, we can even consider the coefficient to be 0 at lambda 0. On the other hand, for m squared, this scale lambda 0 squared is very important, is actually quadratic in it. So that means that arranging, we said we have to, we wanted to, for m squared at lambda 0 to be much smaller than lambda 0 squared. Then arranging this is a fine-tuning. So arranging that this thing is much smaller than lambda 0 squared, when in its running with lambda 0, you have this with lambda squared, we have this lambda 0 squared. Then that means this is a fine-tuning fine-tuning problem. Something that's not natural. And this is, in fact, the reason why people say it is the theory that has a scalar. So, in particular, the Higgs standard model that has a Higgs. We know it has a Higgs. We've measured it. Has a problem in principle. Has a fine-tuning problem because if we integrate up to some higher order scale, we get this quadratic piece, and arranging for the mass that we measure to be much smaller than the scale squared is a fine-tuning. That's something that's not natural. We can also note that we can now define the beta function as usual and calculate it from this relation. So beta of lambda is the derivative of the coupling lambda with respect to log of the scale capital lambda. So we have here log of the scale capital lambda. And so the derivative is, but this is log 1 over capital lambda, so it's minus log. Minus gives plus, so this is plus 3 over 16 pi squared, the coupling squared. The coupling is at capital lambda 0, but to the first order, since we want to keep to consistency in the order, I can replace this. The difference is higher order. So to this one loop order, beta of lambda is 3 over 16 pi squared, lambda squared at the scale capital lambda. All right. So in conclusion, the picture of effective field theory is the following. We define the theory with a real cutoff and with some higher dimensional operators. This is a Wilsonian effective action, which just hides our ignorance about what happens beyond that scale. Then we consider lowering this cutoff by integrating out these intermediate degrees of freedom. When we do that, the coefficients of the Wilsonian effective action change. And in this change, we note that the coefficients of the higher order terms at lambda 0 become irrelevant, so we can put them to 0. So that's why, you know, at our scale, we can say that that we have an effective action that is kind of independent of what is beyond this higher scale. Okay, the only thing that we need to care about is these intermediate modes that over which we can explicitly integrate. Okay, so that's why, let's say, in QCD, we can treat QCD as QCD as long as and integrate from some higher scale that at which we have some other physics in the standard model. We can integrate out that physics without caring what's beyond the standard model. Or then for the standard model, we can integrate out until the point where we're sure we have measured things precisely. Okay, so then this view of effective field theory as a renormalization, which defines renormalization as a change in the cutoff scale, is, well, first of all, so this is the view that Wilson had and led to the renormalization group story, but also will be better defined in the next lecture as what we will be calling Kadanoff blocking. And we will see that this picture also leads to a description of condensed matter theory. Okay. It also allows us to deal in some way with non-renormalizable theories. I mean, in particular, quantum gravity. We know quantum gravity is non-renormalizable, but we can to some degree define what we mean by just regarding non-renormalizable theories as Wilsonian effective action, and then we impose a cutoff, and in this case, the higher dimension coefficients of the higher dimension operator will be proportional to 1 over cutoff to the power delta minus 4, with coefficient smaller than 1. And we can use this effective action below this cutoff. So for when we calculate physics at some energy scale much smaller than lambda 0, the coefficients, then these things are really small because of they vary with the power. So it looks almost like a renormalizable one up to some powers of the energy divided by lambda 0. So they go like lambda. So there's some higher order operators. The higher order operator contributions are powers of the energy divided by lambda 0. Okay, so in that way, we can deal with non-normalizable theories as well. Now, how do we remove the cutoff? Well, so is it possible to completely remove the cutoff lambda 0? Which is to say, is it possible for a theory, some theory that we're looking at, to be consistent at all scales? Well, if we know the exact beta function, we just integrate the defining relation, which is d lambda, the derivative of the coupling with respect to the log of the scale. And then we obtain, so we put b lambda here and then log lambda here, and then we get that integral of d of the coupling divided by beta function between the coupling at m physical and the coupling at lambda 0 is equal to log of lambda 0 over m physical. But then if we want to remove completely, that means going with lambda 0 to infinity, in which case this log is divergent, is infinite, in which case it would mean that also the left-hand side should be infinite. So if it's true that this left-hand side is infinite, then we can completely remove lambda 0. But it could happen that it does not go to infinity, but instead goes to a constant before that. Indeed, this is the case if beta, if this denominator here is positive and increases as the coupling goes to infinity faster than the coupling itself, then d of the coupling over the coupling goes like 1 over the coupling to a positive power at infinity. So that means that it doesn't diverge at infinity. So then this integral is finite in that case. Sorry, what am I saying? Yeah, it's finite at infinity. So then that means that there must be a maximum capital lambda maximum, which is given by this, the integration of d of the coupling of beta function up to infinite coupling. And this would be log of this maximal scale divided by m physical. And for instance, if I use the one loop beta function, which is proportional to the coupling squared, I get that lambda max is m physical exponent of 16 pi squared over 3 lambda physical. That's just the Landau pole that we already explained it a few times. On the other hand, if beta is positive but goes at infinity slower than the coupling, then that means that at infinity I have a positive, the integral gives a positive power of the coupling, so diverges. So then this integral is infinite. So I can put capital lambda 0 to infinity as well. Okay, and can just I can just remove it. So that corresponds to having a new v fixed point lambda star, because that means that that means that for lambda going to lambda star, so I have the integral from lambda to lambda star. Will go to infinity. So if I put lambda of infinity, I call it lambda star, then this is infinite, and then this, if this integral diverges, then that is a UV fixed point. Okay. And that's what happens, for instance, in QCD when I have a free UV fixed point. All right, the Gaussian fixed point, so lambda star equals 0. Okay, so I think that's everything that I wanted to tell you today. Are there any questions? Can somebody check that they can still hear me? Okay, good. So that means, I guess, that you have no questions. So I'll see you on Thursday at 9, where we'll continue with Kadanoff blocking and the connection with the connection of the normalization group with condensed matter. All right. Bye.